to study the Wein'S bridge oscillator. The Wein's bridge oscillator is the most popular audio frequency singular generator circuit. It possesses a good frequency stability, so it is basically very much stable and can give very low distortion also. It is used to measure frequency and capacitance also, right? This is the range for the frequency, and formula uses 1 by 2 pi R1, R2, C1, C2. That you will try also later on. You will see this parameter we will try. This is the Wein's bridge oscillator. So that is this one. So here we will try to select the resistances and capacitance for different type of variation we can take, like R2 C2 you can take, right, and R2 this one you can take Y as a Y capacitor, right, and R2 Z, it up to you. Any combination you can take. Different type of combinations you will pick, right? R1 is fixed, C1 is fixed, and this can be varied. You can see what you will do. So that is the combination. So I have picked this as a resistance, and this as a capacitance in one as a combination of parameters. So now precaution is that if we are getting a large error, then that due to the calibration of CRO, we will see later on that the calibration of CRO switch we should not change, right, because then the calibration will be changed, then the error possibility of error is large. Similarly, the voltage supplied, right, the frequency of that should be constant, that is sometimes varying. You can also select at least 4 combinations for resistances and capacitance or more. Means this one, anything you can take. Similarly, here also three different variations are available. So any 4 combinations you can take, one from here, and second from here, and so on. In this way, different combinations we can. Now here is this is calibration. So you can't change it. Once it is set, right? Calibration, with the calibration you can set it. Once set, don't touch this one or this switch. This will change the calibration. Now suppose this is the time per division, right? This is a switch. Suppose 0.2 is a selection. Suppose 0.2 millisecond, right? So total number of this is for the one big circle, 0.2. So one small division is 1, 2, 3, 4, 5. So 1.2 by 5 means 0.04 millisecond is the basically this one small division. And the like this one complete cycle you can take. If you want to measure one complete cycle, right, you can measure. So that is one division is there, second division, third division, right, and then the fourth division is, fifth division is there, sixth is there, 7 is there, the 7.5. So total number of divisions from here to here are 7.5 small divisions. We can use these measured values, experimental values, right, for the purpose of calculation. You will see later on. This is the total number of cycles in a particular cycle you can count, right. Here we can start. Anyway, you can start wherever this line is exactly at this point where you can start. Means here it is very difficult to start because this line is slightly outside, right. So any way you can start. The purpose is we have to start from here, like start here, goes here, and then here up to this. That is a one cycle. Similarly, here also you have started from here. You can see here also. You start from here, goes like this one. After this is a one complete cycle. That is second reading. In this way, this is third reading. Third reading means the resistances and capacitances, right? Different as in the reading 2, that those combinations that you have taken. Similarly, for reading 4 also, same way, total number of divisions, right? In a particular cycle. From here you can start, no problem. If start from here, here it will finish. If start from here, here it will finish. If it start from here, here it will finish. That is one complete cycle, right? That you can measure. So this is the basically these are the resistances and capacitors I have taken for the reading 1, 2, 3, 4. Accordingly, frequencies you can calculate also. R1, C1 are constant values that is given in the on the kit also. Those values are fixed, right? We can put F is equal to 1 by 2 pi R1, C1. Those are values. These values you will put and root R to C2 kilohertz. And this is a frequency calculated with the theoretically calculated 3.75 kilohertz and so on, like this one. Now this is the basically the when we measure with the CRO. You can see one division of CRO is basically that is 0.2 milliseconds. Right? Number of small division basically 5 are there. So value of one small division is 0.2 divided 5, 0.04. Means whole of the experiment this value I am taking. Okay, so this is reading, different readings are there. So for the first reading, first combination, 7.5 divisions are the number of divisions for one complete cycle. So the time period will be 7.5 multiplied by 0.04. Here also 9 multiplied by 0.04. In this way, this is 0.30 millisecond. This is 0.36 milliseconds. This is 0.32 milliseconds and 0.40 milliseconds. Accordingly, we can convert also. We can convert the time period to the frequency. So that is 1 by t. In this, these are the values. Okay, this is the frequency we are getting corresponding to first combination of R1, R2, like that one, right? Whatever the resistances and the capacitance you are taking. Accordingly, second value will be there, third value will be there, and the fourth value is there. You can see theoretical values we have calculated in the previous slide. So you can see here the values are approximately same, 3.3, 3.75, right? Okay, 2.28, 3.06, 3.13, 3.39, 2.50, and 2.77. In this way, we can see that the values measured, right? Frequency measured with the help of this generator, right? Main generator, right? And the theoretical values are approximately same. So this is basically is an instrument used to measure the frequency also. And generator also very good generator, right? Very less distortion are there. Okay, so these are the purpose of calibration. Don't touch these calibration the points. Once once you have calculated the CRO, then don't touch these points. If you change it, rotate it, right? The whole experiment you have to repeat again, right? You have to set first this the frequency. You have to set it, right? So that error measured is less error is there, right? In this way, that way. That is the basically video of measured values. Okay, you can see now this company I am taking this one and this one. You see that this is a graph. So accordingly we can measure. This is the frequency you can note from here. What is the frequency? Then you can measure cycle also. Then you can change for the second reading. I have this is R1. This value of resistance I have taken, and this value of capacitance I have taken, right? And accordingly, so this values you can measure this tiny part division and this graph also. Then you can take the third reading also, and so on. These type of readings you can take. Then as shown above in table, you can calculate the frequency also, time period also, that you can measure with the help of this combination of Wein'S and this CRO. Thanks.